Okay, so here is the last example that we'll do. So just reading through the problem, it says that a rocket is launched vertically from the ground and a camera is positioned 5,000 feet away from the launch pad, so the place that it launches from. And when the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. And now we want to find the necessary rate of change of the camera's angle at that moment so that it stays focused on the rocket. So we want to draw a picture of this. And okay, so we'll have a rocket taking off. So let's say this is our launch pad. Right. And 5,000 feet away from that is a camera, right? So the distance between these is 5,000, and the rocket launches vertically, so it's going to go straight up in this direction, and we want to know what the angle is that the camera has to tilt to be pointed straight at the rocket. So if we imagine the line of sight of the camera straight to the rocket right here. Okay, so the angle would be the angle between the ground and that line of sight, right? Okay, now one thing I will say is that when you're setting up a problem like this, you might not draw the exact perfect picture the first time, so be willing to like erase your picture and revise it as you try to add more details to it. And on that note, it's probably good to use a pencil in this case, or you could just scribble it out, but I mean, I think using pencil is better. Now, okay, we've drawn our picture, and next we want to label our variables. I actually already labeled the angle theta, so let's go ahead and use that. So notice that theta, that angle, will be changing as the rocket goes up, and that is what we're trying to find, the rate of change of that angle, right? So we have theta. This will be the angle of the camera. And remember, in calculus, we're always going to use radians for the measure of the angle. So just make a note of that. And then the other thing that's changing is the height of the rocket. So we'll use h for that. Height of the rocket. Okay, and those are only two quantities that are changing. So those are our two variables. And I think we've already labeled, yeah, our 5,000 feet on there, so we don't need to label anything else at the moment. Okay, next, we write down what we're given and what we want. So we're given in the problem, let's go through here. This is already on our diagram, so we'll skip that. When the rocket is 1,000 feet above the launch pad, so that's saying that the height of the rocket is 1,000 feet, so that's one piece of information. And then also it says that its velocity is 600 feet per second. Now the velocity is going to be the same as the change in height because the rocket is going only straight upwards, so velocity and the rate of change of the height are exactly the same thing. So here that means dh dt we're given is 600. Right. Okay, so those are the two quantities we're given, and then we want to find the rate of change of the camera's angle. So that will be d theta dt. Okay. Let's see. Now we have done that, and we want to find an equation that relates our variables. So I forgot to label this one. So that is h, And the easiest way to relate these is to use tangent of theta. So tangent of theta is equal to h over 5,000, right? So it's the opposite over adjacent. So you could have, well, anyways, anything else that you would have tried would have been more complicated than this. So this is the best formula to use. Okay, so that is our formula. And then we want to differentiate it. So on the left-hand side, remembering that we're differentiating with respect to time. So let me just write down that step. So we're taking the derivative with respect to time, and both of these, theta and h, are functions of time, so we have to use a chain rule. So first we get secant squared theta, that's the derivative of tangent, and then we get times d theta dt. Here, that 1 over 5,000 is a constant that we can leave out front, and then we have the derivative of just h, so that is going to be dh dt. Okay, so there is our equation. Now what we want to do next is plug in our given quantities and solve for d theta dt. Now we are given dh dt, but we're not given the value of theta or the value of secant squared of theta, right? So what we need to do is figure that out using the fact that h is equal to 1,000. So we want to figure out what is secant squared of theta when h is equal to 1,000, right? And we can do that using trigonometry. So just redrawing our triangle, right? That 5,000 feet never changes, so that's going to be there. And then we have 1,000. So we're given that h is equal to 1,000. And then we just want to figure out what secant will be. And so looking at this and remembering that secant is equal to the hypotenuse over adjacent. If we want to figure out what the value of secant of theta is, we just need to figure out what the hypotenuse is, because we already know the value of the adjacent side is equal to 5,000. So it's just a matter of figuring out what that is. So I'm going to label that x, and we want to solve for x in order to figure out what secant of theta is, right? And since this is a right triangle, we can use the Pythagorean theorem to figure this out. So we're given 1,000 squared plus 5,000 squared, right? And since multiplying these out would just give you a ton of zeros, I'm going to actually just factor out a 1,000 squared from each of these, which will make it a little bit easier to write down. Okay, so 1,000 squared, and then this is going to be 26, right? Okay, so to get the value of x, we can take the square root of both sides and remember that x will be positive, so we don't need a plus or minus in this case. 1,000 squared times 26, and so we can rewrite that as 1,000 times square root 26, right? Okay, so that means that our value of secant of theta is going to be, as we said, x over 5,000, and x is equal to 1,000 root 26 over, or that's what x is equal to, and then we'll take it over 5,000, and then we get a bunch of these zeros canceling, which is nice, and we get just root 26 over 5, right? Okay, so we can go ahead and plug that in. Now in this equation, that's where we want to plug it in. We get this is secant squared theta, so we'll take our secant theta and square it. D theta dt is what we're solving for. And then this is equal to 1 over 5,000. And dh dt was given, it's up here, it's 600. Right. Okay, so we would get 26 over 25 d theta dt is equal to 6 over 50, right? And then we would want to multiply by both sides by 25 over 26 to get d theta dt by itself. So, okay, I'll do this in 2 steps. 6 over 50 times 25 over 26, and then we can cancel some and then get 3 over 26. Okay. So that is going to be our answer. D theta dt is equal to 3 over 26, and remembering that theta was measured in radians and time was measured in seconds. So we can tell that from how the velocity was given. So our answer is going to be 3 over 26 radians per second. Okay, so that is all for this section.